On July 1st, 2025, a survey telescope in the mountains of Chile caught a faint point of light moving against the stars. At first, it looked like an ordinary comet. Its orbit said otherwise. When astronomers reconstructed the path, they found that it had approached the Sun already unbound. It was not following a long ellipse that would eventually bring it back. It was crossing the solar system on an open hyperbolic trajectory, carrying an incoming speed that no encounter with the known planets could explain. It had arrived from interstellar space, and after one passage through the inner solar system, it would leave again forever. The Sun did not capture it. The Sun alone could not capture an object arriving this fast without some way to remove enormous energy, and no such encounter occurred. By the time you are watching this, the comet is outbound, slowing as it climbs away from the Sun, but still moving fast enough to escape permanently. We call it 3I/Atlas, the third confirmed interstellar object ever detected. It formed around another star. It may have traveled through the Milky Way for billions of years, and during the few months when sunlight awakened its buried ices, humanity turned an extraordinary network of instruments toward it. Hubble, Webb, SPHEREX, TESS, giant radio arrays, telescopes in X-ray light, spacecraft near Mars, a probe traveling toward Jupiter, and even a mission on its way to Europa. Together, they did more than photograph a comet. They measured water, carbon dioxide, methane, metals, organic molecules, dust, and rare isotopes. Those chemical fingerprints point toward a birthplace far colder than the region where our own comets formed, and possibly toward a planetary system that existed billions of years before the Sun. The measurements are real. The proposed age is an interpretation, not a directly measured birthday. This is the complete story of how we know 3I/Atlas came from another star, what it carried, what remains uncertain, and why a natural fragment of another planetary system may be more scientifically valuable than any sensational story built around it. Our Sun follows a closed orbit unless a later gravitational encounter changes it. Planets, moons, asteroids, and ordinary comets trace ellipses around the Sun. Even a comet that disappears for thousands of years remains tied to the solar system by gravity, still on a leash, however long. The way you tell whether something is bound is by measuring the shape of its orbit. Astronomers describe that shape with a single number called eccentricity. A perfect circle has an eccentricity of 0. A stretched out ellipse, a long, looping comet orbit, has a value approaching 1, but still below it. Anything genuinely tied to the Sun stays under that line. When astronomers reconstructed the path of the object discovered on July 1st, 2025, the osculating eccentricity was not merely a little above 1. It was around 6.1. An eccentricity above 1 describes a hyperbola, an open path, rather than a closed ellipse. But eccentricity alone needs context. A solar system comet can, in principle, be thrown onto a slightly hyperbolic outbound path by a close encounter with a planet. What proved the interstellar origin of 3I/Atlas was its original inbound trajectory, calculated in the solar system's center of mass frame before any close planetary encounter. Together with its enormous hyperbolic excess speed of roughly 58 kilometers per second, it approached the planetary region already unbound. The Sun bent its path and accelerated it on the way in. But a two-body encounter with the Sun cannot permanently capture an object unless energy is removed. No planet or other mechanism removed enough energy. 3. I/Atlas was a visitor before it reached us, and it remained a visitor afterward. It was discovered by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a NASA-funded network built to spot asteroids that might threaten Earth. One of its telescopes, at Rio Hurtado in Chile, caught the object first and reported it to the Minor Planet Center on the 1st of July 2025. At that point, it was far out, around the distance of Jupiter's orbit, just a tiny speck moving a little too quickly and along a slightly wrong line. To see whether other instruments had recorded it before anyone knew what it was, they found an unusually rich pre-discovery trail. Vera C. Rubin Observatory recovered it in commissioning images from June 21st, 10 days before discovery. NASA's Planet Hunting Test Satellite had crossed the same region even earlier, between May 7th and June 2nd, when the object was roughly 6 astronomical units from the Sun. Those stacked TESS images suggested that it may already have been active at that distance, although individual exposures were too faint to reveal the nucleus or a secure rotation period. Extending the measured arc backward made the orbit dramatically more precise and strengthened the interstellar verdict. The name it received follows a simple logic. The number 3 marks it as the third confirmed object of its kind. The letter I stands for interstellar, and Atlas credits the survey that found it, 3I Atlas. Before that formal designation, it carried a provisional comet name, C/2025N1. Its full orbital solution confirmed just how extreme the encounter was. The eccentricity settled near 6.1, much larger than the values for the previous 2 interstellar objects. The orbital inclination was about 175 degrees, meaning it approached on a strongly retrograde path, almost opposite to the direction the planet's orbit. Far from the Sun, where solar gravity contributes little to the speed, its hyperbolic excess velocity was about 58 kilometers per second. An object ejected from a known planet in the modern solar system could not plausibly approach from interstellar distance with that incoming speed. Its closest approach to the Sun, called perihelion, came on October 29, 2025, at about 1.36 astronomical units, or roughly 203 million kilometers. That carried it just inside the average orbit of Mars, not close to Earth. It passed about 29 million kilometers from Mars on October 3rd, allowing Mars Express and the ExoMars Trace Gas Orbiter to view it from a valuable angle. Measurements from ExoMars helped improve predictions of the comet's position by roughly a factor of 10. Its closest approach to Earth came on December 19th, at about 1.7 to 1.8 astronomical units, around 270 million kilometers away. It is worth saying this plainly, because sensational headlines suggested otherwise. 3I/Atlas was never a threat to Earth. Its path was known with precision within weeks of discovery, and at no point did that path bring it into dangerous territory. The only thing it endangered was a few of our old assumptions. By the time it rounded the Sun and moved outward, the central question had changed from where did it come from to what did it carry. Solar heating altered the outer layers and released gas and dust, but the deeper material still preserved a sample of another planetary system. As 3I/Atlas climbs away, solar gravity is slowing it from the greater speed it reached near perihelion. It is not accelerating outward, but it remains unbound, and far from the Sun, its speed will approach essentially the same hyperbolic excess value it had on arrival. There is no closed orbit and no return visit. The encounter was a single crossing through our system, but not before we read some of them. So what did this visitor carry from its lost home system? The third visitor. To understand why 3I/Atlas mattered so much, you have to understand how little we had to compare it to. For most of history, interstellar objects were purely theoretical. Astronomers were confident they must exist. Every planetary system, as it forms, should fling a portion of its material out into the galaxy. Leftover icy and rocky bodies thrown away by the gravity of growing planets. Multiply that by the hundreds of billions of stars in the Milky Way, and interstellar space should be full of these castaways drifting between the stars. But predicting them and catching one are very different things. They are small, dark, fast, and they do not announce themselves. For decades, we saw none. Then, in October of 2017, the first one arrived. It was called 1I/ʻOumuamua, a Hawaiian word often translated as a scout or a messenger arriving from afar. And it was strange from the very start. It was discovered only after it had already rounded the sun and was heading back out, which left astronomers a painfully short window to study it. ʻOumuamua showed no coma, no fuzzy cloud of gas and dust, none of the obvious signs of a comet. It looked more like a bare rock. Its brightness swung up and down dramatically as it tumbled, which told astronomers it was elongated. But exactly how elongated and what shape could not be pinned down. The popular image of a long, cigar-shaped object is one artist's interpretation, not a confirmed fact. It might have been shaped more like a flattened disc. We genuinely do not know, and because it is now gone, we may never know. Then came the real puzzle. As ʻOumuamua left, its path showed a slight extra push, a small acceleration that gravity alone could not explain. In comets, that kind of push is normal. It comes from gas jetting off the surface as ices heat up. But ʻOumuamua showed no visible outgassing at all. The push was there, the obvious cause was not. That single, unexplained nudge launched years of debate and a swarm of hypotheses, some sober and some sensational. The honest scientific position on ʻOumuamua is humility. It was our first, it was faint, it left quickly, and it kept most of its secrets. 2 years later, in August of 2019, the second visitor appeared, and it could not have been more different. 2I/Borisov was discovered by an amateur astronomer, Gennady Borisov, using a telescope he had built himself. And crucially, it was found on its way in, giving astronomers months to watch it. Its orbit was clearly hyperbolic, its interstellar origin beyond doubt. Borisov was unmistakably cometary. It had a bright coma and a tail, and sunlight drove familiar outgassing. Yet even Borisov was not chemically identical to a typical solar system comet. Measurements found unusually abundant carbon monoxide in parts of the observing campaign, suggesting formation in a very cold region around its parent star. Its behavior was legible, but its chemistry already warned that the word comet covers a wide family rather than a single standard recipe. So by the middle of 2025, that was the entire catalogue. 2 objects, one inscrutable and gone, one comet-like and also gone. 2 data points, wildly different from each other, hinting at a population we could barely characterize. And then 3I/Atlas arrived. It was found before perihelion, active while still far from the sun, and bright enough for months of coordinated work. The pre-Covery record extended back to May. Observations continued through solar conjunction from spacecraft away from Earth, and post-perihelion instruments watched the comet cool and change. Instead of a hurried snapshot, astronomers obtained a time series, a chemical and physical story unfolding as sunlight reached progressively less volatile ices. This is why only 3 objects have been confirmed in 8 years, and why each one matters so enormously. It is not that interstellar objects are rare in space. The problem is detection. They are small, often just a fraction of a kilometer across. They are dark, they move fast, and they are only bright enough to see for a brief window near the sun. To catch one, a survey has to be scanning the right patch of sky at the right moment and recognize from a faint moving dot that this one is different. For most of astronomical history, we simply lacked the tools. We were almost certainly being visited the entire time, and we never saw the visitors. 3I/Atlas arrived at exactly the moment our telescopes were finally good enough to give one a proper examination. The discovery history itself demonstrates the selection effect. TESS had recorded the object nearly 2 months before discovery, but only after astronomers knew the orbit could they stack many faint images along the predicted path and recover it. Rubin Observatory had also photographed it during commissioning. The object was present in the data. What was missing was enough signal and context to recognize it in real time. Estimates depend heavily on the assumed size distribution, brightness, activity, and survey efficiency. So published numbers span wide ranges. The 3 detections nevertheless imply an enormous galactic population of ejected planetesimals. Many small interstellar bodies should pass through the solar system unnoticed, while larger or unusually active objects are easier to find. The 3 confirmed visitors are not a representative census. They are the few objects that cross the narrow intersection between being close enough, bright enough, and observed at the right time. It arrived bright enough and active enough for the most detailed chemical study of an interstellar object ever attempted. Reading an alien comet. No spacecraft was positioned to rendezvous with 3I/Atlas after its discovery. It was moving too quickly, the warning time was too short, and matching its trajectory would have required far more launch energy than an ordinary planetary mission. Everything we learned during this passage came from remote sensing, catching its light, separating that light by wavelength, and observing the coma from many locations across the solar system. That turns out to be a great deal. The investigation unfolded over months, and it is best understood as a story, not a list, a picture assembled piece by piece as the object moved closer to the sun and its activity grew. The first task was to see the comet clearly. On July 21, 2025, the Hubble Space Telescope observed it while it was still far from the sun. Hubble revealed a compact, teardrop-shaped cocoon of dust around the hidden icy nucleus and a faint tail. Ground-based imaging had already resolved a coma, and Rubin data showed a large dust-scattering cross-section relative to any plausible bare nucleus. In its basic physical behavior, the interstellar visitor was acting like a natural active comet. Hubble also confronted the first hard problem: how big is it? And here we run into a limitation that shapes everything. The solid nucleus of a comet is tiny, and it sits buried inside a glowing cloud of dust that is far larger and far brighter. Even Hubble could not see the nucleus directly. What it could do was set limits. Based on those observations, the nucleus was estimated to be no smaller than a few hundred meters across, and no larger than a few kilometers. The official figures place the diameter somewhere between roughly 440 meters and 5.6 kilometers. That is a wide range, and the width of it is the point. When people ask how big is 3I/Atlas, the honest answer is that we know the size of its glowing coma very well, and the size of its actual solid body only within loose bounds. Later post-perihelion analyses, using brightness, activity models, assumed reflectivity, and the comet's small non-gravitational acceleration, favored an effective radius around 1.3 to 1.5 kilometers. That is a model-dependent estimate, not a direct image of the surface. No telescope ever resolved the solid surface. This distinction between what we measured of the coma and what we inferred about the nucleus runs through the entire investigation, and it matters. As the object drew closer and warmed, the deeper work began, taking its light apart to read its chemistry. This is done with spectroscopy. Every gas, when it glows or absorbs light, leaves a specific pattern of lines, a chemical fingerprint. By spreading 3I/Atlas's light into a spectrum, astronomers could identify exactly which gases were streaming off it, and in what proportions. The observing campaign became one of the most geographically distributed comet studies ever attempted. Webb obtained infrared spectra before and after perihelion. ALMA measured molecules at millimeter wavelengths. The Very Large Telescope and other ground observatories followed the gas, dust, metals, color, and changing activity. As Earth lost sight of the comet near the Sun, spacecraft elsewhere took over. Mars Express and the ExoMars Trace Gas Orbiter observed it around its October 3rd passage near Mars, and ExoMars astrometry sharpened the predicted path. NASA's MAVEN Orbiter and China's Tianwen-1 also contributed observations from Mars, with the Tianwen-1 geometry helping researchers constrain properties of the coma's dust from outside the comet's orbital plane. Solar missions including STEREO, SOHO, and Parker Solar Probe monitored the comet around the period when glare made ordinary Earth-based observing difficult. Parker alone collected roughly 10 images a day from October 18th through November 5th. In November, ESA's JUICE spacecraft observed 3I/Atlas while traveling toward Jupiter. JUICE came within roughly 60 million kilometers and used cameras, spectrometers, and a particle instrument. Its first analyses found strong water and carbon dioxide activity. On November 2nd, the MAGIS spectrometer inferred water vapor production near 2,000 kilograms per second, while another instrument found that much of the water was released toward the Sun, and that a substantial fraction probably came from icy grains in the coma, rather than directly from the nucleus. NASA's Europa Clipper also turned its ultraviolet spectrograph toward the comet for 7 hours on November 6th, from about 164 million kilometers away. Hubble returned on November 30th. Spherics observed a pronounced infrared brightening in December and mapped dust, water, carbon dioxide, and organic features. TESS then conducted a dedicated observing run in January 2026 to study activity and search for rotational modulation. The campaign also moved beyond visible and infrared light. XRISM and XMM Newton detected a diffuse X-ray glow, making 3I/Atlas the first interstellar comet observed in X-rays. Such emission does not mean the nucleus itself was hot. Cometary X-rays are generally produced when highly charged solar wind ions exchange electrons with neutral gas in the coma. Each observatory was seeing a different consequence of the same process. Ancient ice being transformed into an enormous temporary atmosphere by a star the comet had never approached before. What emerged was a portrait of a comet that was, in its ingredients, both familiar and strange. When Webb observed it well before perihelion, still relatively far from the Sun, the coma was dominated by carbon dioxide, with water present in smaller amounts. The ratio of carbon dioxide to water was among the highest ever measured in any comet. This is a real clue, and a subtle one. Different ices turn from solid to gas at different temperatures. Far from the Sun, it is the most volatile ices, like carbon dioxide and carbon monoxide, that drive the activity, because water ice is still too cold to sublimate strongly. As 3I/Atlas approached the Sun and heated up, that balance shifted, and water sublimation grew more important. Watching that transition happen was like watching the comet's chemistry wake up, layer by layer. Across the campaign, astronomers assembled the richest volatile inventory yet obtained for an interstellar object. Secure detections included water, carbon dioxide, carbon monoxide, methane, methanol, hydrogen cyanide or its related CN emission, and hydroxyl produced as sunlight broke water apart. Carbonyl sulfide was reported at lower confidence in early Webb work. Mid-infrared spectra also showed broad organic features, although a spectral feature can identify classes of bonds more readily than one unique complex molecule. The composition changed with distance from the Sun. In pre-perihelion Webb observations at about 3.3 astronomical units, carbon dioxide dominated the gas coma, and the carbon dioxide to water production ratio was about 7.6, among the highest measured in any comet. Highly volatile carbon dioxide and carbon monoxide can drive activity where water ice remains too cold. Near and after perihelion, water production became much stronger. Later, Webb observations directly detected methane for the first time in an interstellar object and found that overall gas production declined as the comet receded, with water shutting down faster than the more volatile methane and carbon dioxide. The delayed appearance of stronger methane relative to water was interpreted as possible evidence that the outermost layers had lost methane during earlier processing, while fresher subsurface material became exposed later. The water itself did not all emerge from a single exposed patch on the nucleus. Webb and JUICE mapped an extended source in the coma, consistent with icy grains being lifted from the surface and then sublimating after they had escaped. At the same time, sunward enhanced jets showed that the activity was not perfectly uniform. The nucleus had active regions, changing illumination, and a surrounding halo that could continue producing gas far from the solid body. Detected neutral nickel, while iron became more apparent closer to perihelion. The evolving nickel to iron balance may reflect temperature-dependent release from metal-bearing molecules, or a genuinely different chemical inventory. It is unusual, but not a sign of machinery. Neutral metals have also been detected in solar system comets. Webb's mid-infrared spectrum provided an additional record in the dust. A June 2026 analysis reported that the coma's silicate grains were dominated by amorphous rather than strongly crystalline material. The authors argued that the dust resembled material in the interstellar medium, or the cold outer regions of planet-forming disks, more closely than the crystalline-rich mixtures found in many solar system comets. One interpretation is that the comet formed far from its parent star with little inward-outward mixing. Another is that billions of years of cosmic ray exposure altered originally crystalline grains. The first interpretation was favored in that study, but the result was still new and model-dependent. None of these observations requires exotic physics. Gas production, jets, dust, solar wind X-rays, fading with distance, and small non-gravitational accelerations all fit the behavior of a natural comet. What made the object extraordinary was not a violation of the rules. It was that the ingredients had been assembled under rules operating around another star. And when researchers looked closely at the finest detail of that chemistry, not just which molecules were present, but which versions of them, they found something that pointed to an origin far colder and far older than our Sun, older than the solar system. To understand the most remarkable claim about 3I/Atlas, you need one idea: isotopes. Most chemical elements come in slightly different versions, called isotopes, that differ only in weight. Ordinary hydrogen has a heavier cousin called deuterium, carrying an extra neutron. Carbon comes mostly as carbon-12, with a rarer, heavier form called carbon-13. Chemically, these versions behave almost identically, but the ratio between light and heavy versions is set by the environment where the material formed, above all by temperature. That makes isotope ratios a kind of thermometer, frozen into the ice. Measure the balance of heavy to light hydrogen locked in a comet's water, and you are reading the temperature of the place that water first froze billions of years ago. The ice remembers. When Webb measured the water in 3I/Atlas, it found something striking. The deuterium to hydrogen ratio in water was reported near 0.95%, with an uncertainty of about 0.06 percentage points. That is more than an order of magnitude above known solar system comets, and is often summarized as roughly 30 times the typical cometary value. Independent analyses using other data return slightly different central values, but the conclusion of extreme deuterium enrichment is robust. Here is why that matters. Deuterium becomes strongly enriched in particular molecules through low-temperature chemistry in dense interstellar clouds and the cold outer regions of protoplanetary disks. A high ratio can survive when ice remains cold and avoids extensive later reprocessing. Models applied to 3I/Atlas point toward formation at around or below 30 Kelvin, about minus 243 degrees Celsius. That temperature is inferred from chemical models. It was not measured with a thermometer at the comet's birthplace. Webb also detected deuterated methane. The methane deuterium to hydrogen ratio was reported near 3.3%, about 14 times the value measured in methane at Comet 67P by Rosetta. The relationship between methane and water deuteration was broadly consistent with both molecules inheriting a highly deuterium-rich chemical environment. This was the first such isotopic measurement of methane in an interstellar object, and reinforced the conclusion that the comet formed in conditions very different from those that produced the Sun and planets. The carbon told a complementary story. Webb measurements placed the carbon-12 to carbon-13 ratio in broad ranges around 123 to 191, depending on whether carbon monoxide or carbon dioxide was used. These values were higher than typical solar system comet values and higher than many measurements of the nearby interstellar medium today. Very large telescope observations of CN found a carbon ratio broadly consistent with that picture, and a nitrogen-14 to nitrogen-15 ratio with large uncertainty but a central value above the usual solar system comet range. Together, the isotope measurements pointed toward cold outer disk chemistry around an older, relatively metal-poor star. The nitrogen result was less precise, so it should be treated as supporting evidence rather than a standalone verdict. The balance of carbon isotopes in the galaxy is not fixed. It changes over cosmic time. Each generation of stars forges elements and enriches the galaxy, gradually shifting the carbon ratio as the universe ages. So the carbon signature of material is, loosely, a clock, one that reflects how much stellar processing the galaxy had undergone when that material formed. When researchers compared the carbon measurements with models of galactic chemical evolution, the results suggested formation early in the Milky Way's history. A peer-reviewed analysis concluded that the comet could have accreted roughly 10 to 12 billion years ago, during the broad era sometimes called cosmic noon, when star formation across the universe was near its peak. 12 billion years. If that interpretation holds, this object formed when the universe was young, billions of years before the sun, before the earth, before any of the atoms in your body had been gathered into a star. It would be a preserved fragment of an ancient planetary system that may no longer even exist, drifting through the galaxy since a time when the Milky Way itself was a very different place. There is a second, independent line of reasoning that points the same direction. The way 3I/Atlas moves through the galaxy, its velocity relative to the general population of stars, can be used to estimate a kinematic age. Objects that have been drifting for a very long time tend to have been gravitationally stirred onto faster, hotter orbits. That analysis gave an age range of roughly 3 to 11 billion years, making 3I/Atlas plausibly the oldest interstellar object we have seen. Two different methods pointing toward great antiquity. But this is the centerpiece of the documentary, and it is exactly where honesty matters most. So let me be precise about what is known and what is inferred. What is directly measured is the chemistry, the deuterium enrichment, the carbon isotope ratios, the metal content. Those are observations made with world-class instruments, and they are robust. What is measured is that 3I/Atlas is chemically unlike any body from our solar system, and that its ices formed in extreme cold. The age is not measured. Nobody read a birthday off this comet. The 10 to 12 billion year figure is an interpretation, the output of models of how the galaxy's chemistry has evolved, applied to the isotope measurements. Those models carry assumptions and uncertainties. Different models or refined measurements could shift the number. The kinematic age is likewise a statistical estimate with a wide range, not a precise value. When you see a confident headline declaring this comet is 12 billion years old, understand what sits underneath it. A genuinely extraordinary set of measurements, plus a chain of reasoning that is strong but model dependent. That does not diminish the result. It sharpens it. The water, methane, carbon, and nitrogen isotope measurements are real. The cold birthplace is a strong interpretation supported by several independent chemical traces. The 10 to 12 billion year age is a model-based possibility, while the kinematic estimate remains broad. The amorphous dust mineralogy offers another potentially compatible clue, but it too has alternative explanations. A responsible conclusion is therefore precise. 3I/Atlas formed in an unusually cold chemical environment and is very likely older than the solar system. It may be an ancient survivor from the early Milky Way, but its exact age has not been measured, which raises the next question. If it formed around another star so long ago, how did it end up here? Thrown between the stars, every comet begins the same way, in the cold outer reaches of a young planetary system. where gas and dust swirl around a newborn star in a vast disk. In that disk, ice and dust stick together into ever larger clumps, and some of those clumps grow into comets and the cores of planets. This is planet formation, and it leaves behind an enormous population of small, icy bodies, the leftovers. Those leftovers are not safe. A young planetary system is a gravitational battlefield. As giant planets grow and migrate, their gravity flings smaller bodies around violently. A comet that passes too close to a massive planet can be whipped onto a new path, sometimes inward, sometimes outward, and sometimes so hard that it is thrown out of the system entirely, past the point of no return, into interstellar space. That is the leading family of explanations for how 3I/Atlas began its journey. It likely formed in the cold outer region of another star's disk and was later ejected by gravitational scattering. A giant planet could have provided the final kick. Migration or instability among several planets could have repeatedly altered its orbit. In a binary system or a crowded stellar birthplace, a companion star or a close stellar flyby could also have helped strip small bodies away. The data do not identify which mechanism operated in this particular system. Once free, it became a castaway, and the journey that followed is almost impossible to comprehend. It drifted through the galaxy for what the evidence suggests was billions of years, through the near-perfect vacuum and cold of interstellar space, exposed to starlight and the steady sleet of cosmic rays. Those cosmic rays slowly process the outermost layers of such an object, altering its surface chemistry over eons. But deeper down, shielded, the primitive ice can survive almost unchanged, which is exactly why these objects are such precious samples. Beneath a weathered crust, they can preserve material in nearly the state it formed, a frozen record of another system's birth. And here we reach one of the hardest limits in this entire story. We do not know which star 3I/Atlas came from. We cannot point to a spot in the sky and say, there, that is its home. The reason is time and motion. Over billions of years, both the comet and every candidate star have moved enormous distances around the galaxy. The galaxy has turned many times, tracing the object's path backward with enough precision to match it to a specific star across that much time and that much motion is currently beyond us. The same problem defeated attempts to find the home stars of the first two visitors. 3I/Atlas's origin system remains unknown and may always remain unknown. It is a letter with no return address. The same uncertainty affects estimates of how many interstellar objects exist. Detection of 3 visitors does not translate cleanly into one number because each survey has different sensitivity and each object has different size and activity. Some models imply an astonishing galactic inventory, but the total can change by orders of magnitude if the assumed size distribution changes. What is secure is the qualitative conclusion. Ejection from planetary systems should create a vast population, and our confirmed sample is strongly biased toward objects that happen to become detectable. That uncertainty, the genuine gaps in what we know, is also where a very different kind of claim tends to rush in. Whenever an object is unusual, and especially when it comes from beyond the solar system, some will suggest it is not a natural object at all, but a piece of alien technology. It is worth addressing that directly and fairly. The scientific answer is clear, and it is not based on closed-mindedness. It is based on evidence. Everything observed about 3I/Atlas is consistent with a natural comet. Its hyperbolic orbit is not exotic or suspicious. It is exactly what an interstellar object should have, the natural signature of something not bound to the sun. Its behavior, the coma, the dust, the outgassing, the shifting balance of gases as it warmed, is comet behavior. Radio astronomers deliberately tested that possibility. The Allen Telescope Array began observations within days of discovery across frequencies from 1 to 9 gigahertz. Meerkat data detected hydroxyl associated with water chemistry, while a parallel technosignature search found no artificial emission. Murayang at Parkes and the Green Bank Telescope observed later, including near the laser-like transients. No technosignature was found. The searches cannot prove the absence of every conceivable technology, but they found no evidence that requires an artificial explanation, while the cometary evidence is extensive and direct. This is the crucial distinction. Unusual does not mean artificial. 3. I/Atlas is genuinely unusual, chemically unlike our own comets and probably far older. But unusual is a statement about how it compares to the small sample we know, not evidence of design. A scientific hypothesis makes testable predictions and survives contact with data. The artificial origin claims, when tested against the data, simply do not hold up. There is no observation that requires them, and several that argue against them. Treating unsupported speculation as equal to the weight of evidence would not be open-mindedness. It would be a failure to look honestly at what the object actually shows. What 3 I/Atlas actually shows is something in its way more profound than a spacecraft. It is a real, physical piece of another planetary system, cold, ancient, natural, that crossed the galaxy and let us examine it. And it raises a quiet, staggering possibility. Interstellar space may be full of these castaways. Depending on their size distribution, small ones could pass through the solar system frequently while remaining invisible. For every visitor we confirm, an unknown number may cross unseen, silent, and dark. The exact rate remains uncertain, but the mechanism that creates them operates wherever planetary systems form. The messages between worlds. Step back and consider what 3 I/Atlas really represents. For all our progress, humanity has never sent anything to another star system, and will not for a very long time. The distances are simply too vast. The nearest stars are years away even for light, and lifetimes away for any craft we can build. The material of other planetary systems has always seemed permanently out of reach, something we could only study from afar as points of light. 3 I/Atlas quietly overturns that. We could not go to another star system, so a piece of one came to us. That is why these objects matter so much to science. Everything else we know about other planetary systems, we know indirectly, by watching a distant star dim as a planet crosses it, or by reading starlight filtered through a far-off atmosphere. Those methods are extraordinary, but they are remote. An interstellar object is different in kind. It is not a measurement of another system. It is a piece of one, close enough to read in detail. It lets us test whether the comets of our own system are typical of the galaxy or unusual, whether the chemistry that built our world is common or rare. And here is the humbling part. We now have 3 confirmed interstellar objects, and all 3 have presented different observational stories. ʻOumuamua showed no obvious coma and left its shape and composition unresolved. Borisov was clearly cometary, but chemically distinctive in important ways. 3I/Atlas was active early enough to reveal an unusually rich and ancient-looking chemical record. 3 visitors are far too few to define a population, but they are already enough to destroy the idea that every ejected planetesimal should look the same. Each one may be a fragment of a different planetary system, with its own history, its own temperature, its own age. We are not sampling one population of identical objects. We are sampling the diversity of planet formation across the entire galaxy, one rare visitor at a time. The obvious problem is that 3 is a tiny number, and that is about to change. The Vera C. Rubin Observatory in Chile began its 10-year legacy survey of space and time in June 2026. Its wide field, depth, and repeated scans make it exceptionally capable of detecting fast, faint objects and recognizing them earlier. Rubin had already demonstrated that power by recovering 3I/Atlas in commissioning images 10 days before the official discovery. It is expected to transform the field, although the eventual discovery rate remains uncertain because the population itself is uncertain. If Rubin finds interstellar objects earlier and farther from the Sun, astronomers will gain longer observing arcs, better chemical coverage, and perhaps enough warning for a spacecraft response. More discoveries would also open a door we have not yet been able to walk through, reaching 1. No mission was launched to 3I/Atlas. The comet was found too late and moving too fast for a newly prepared spacecraft to match its path. Scientists have nevertheless studied rapid response architectures, high-energy flybys, and missions that would wait in space for a suitable target. Project Lyra is a family of feasibility studies rather than an approved flight. ESA's Comet Interceptor is a real mission in development, intended to wait near the Sun-Earth L2 region for a suitable, pristine comet. An interstellar target is possible in principle, but considered unlikely and is not guaranteed. A successful intercept would probably be a fast flyby rather than a gentle rendezvous. Even that could image the nucleus, map jets, directly sample dust and gas, measure isotopes with local instruments, and distinguish surface processing from original material. For now though, 3I/Atlas is leaving. It rounded the Sun and is climbing back toward interstellar space, slowing under the Sun's gravity while remaining far above escape speed. As its distance grows, the coma fades and the object becomes harder to observe. The data gathered during the encounter will be studied for years, but the comet itself will not return. It is carrying the rest of its history back into the dark, and much about it remains unknown. We do not know its home star. We do not know the exact shape, spin state, internal structure, or unambiguous nucleus size. Some molecular detections and abundance ratios will be refined as teams complete their analyses. The dust may have been born amorphous or altered during interstellar travel. The age rests on galactic chemistry and kinematic models, not a direct clock. Even the question of whether 3I/Atlas is representative of ancient interstellar comets cannot be answered with a sample of one. It arrived, allowed a brief examination, and left most of its history intact. But think about what it truly was. Not a message. Nobody sent it. There was no intention behind it, no meaning encoded for us to find. It is something more real than a message, and in a way more moving. It is a surviving fragment of a world's beginning. Ice that froze around another star in a cold so deep and a time so ancient that our own sun had not yet been born. It drifted across the galaxy for billions of years, through the dark between the stars, and for a few months it passed close enough for a young species on a small blue planet to turn its instruments toward it and listen. We cannot yet cross the distances between the stars, but the stars, it turns out, send fragments of themselves to us, and we have finally built the eyes to read them. Thank you for spending this time with Beyond the Surface Cosmos. If this journey meant something to you, take a moment to like the video, subscribe to the channel, and share it with someone who looks up at the night sky and wonders what else is out there. There is so much more to explore, and we are only just beginning.